September 20th, 1942. Naval Air Station North Island, San Diego, California. Lieutenant Commander Eddie Sanders walked across the tarmac toward an aircraft that shouldn't exist in American hands. The morning sun glinted off the distinctive lines of a Mitsubishi A6M Zero fighter, its rising sun insignia hastily painted over with American markings. The captured Japanese fighter sat incongruously among rows of Grumman Wildcats and Curtiss Warhawks, a prize almost beyond calculation in its potential value to the war effort. Sanders had test-flown dozens of aircraft types during his naval career. He understood airframes, engine characteristics, aerodynamic principles, but this morning felt different. The Zero represented more than just another foreign aircraft to evaluate. It embodied 2.5 years of Japanese air superiority across the Pacific. It was the fighter that had devastated Pearl Harbor, swept Allied opposition from the skies over the Philippines and Malaya, and established an aura of invincibility that bordered on mythology in the minds of American pilots. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The aircraft had arrived at North Island in August, after an extraordinary recovery operation from Akutan Island in Alaska's Aleutian Chain. Mechanics had spent weeks carefully repairing damage from the crash landing that had killed its 19-year-old pilot, Flight Petty Officer Tadayoshi Koga, during the Japanese attack on Dutch Harbor in early June. Now, after meticulous restoration, the Zero was airworthy again. Sanders would be the first American pilot to fly it. He climbed into the cockpit. The seat sat lower than American fighters. The instruments were labeled in Japanese characters he couldn't read. The control stick felt light in his hand. Everything about the aircraft seemed delicate, almost fragile compared to the robust construction of American designs. At 0840 hours, Sanders received clearance from the tower. He advanced the throttle. The Nakajima Sakai 12 radial engine responded smoothly. The aircraft accelerated quickly down the runway. At 90 miles per hour, Sanders eased back on the stick. The Zero lifted off, with an eagerness that immediately felt unusual. The climb rate was extraordinary. Within minutes of that first flight, Sanders discovered something that would fundamentally alter American fighter tactics for the remainder of the Pacific War. The information would save countless American lives. It would help turn the tide of aerial combat from near parity to overwhelming American advantage. And it would shatter the carefully constructed illusion of Japanese technological superiority that had dominated the first year of the war. But the revelation wasn't what anyone expected. American intelligence had anticipated learning about advanced engineering, secret weapons systems, or revolutionary aerodynamic principles. What they discovered instead was far more devastating to Japanese prospects. The Zero, this fighter that had terrorized Allied pilots across the Pacific, had a fundamental design flaw so severe that it rendered the aircraft vulnerable to weapons the Americans had assumed were completely ineffective against modern combat aircraft. The morning Sanders took that Zero into the San Diego sky marked the beginning of the end for Japanese air power. Not because the Americans had developed a superweapon, not because they had cracked an unbreakable code, but because they were about to learn that the fighter everyone feared was built on a foundation of compromises so extreme that even standard infantry weapons could tear it apart. The Mitsubishi A6M Zero didn't emerge from nowhere. Its development began in 1937, when the Imperial Japanese Navy issued specifications for a carrier-based fighter to replace the aging Mitsubishi. The requirements seemed almost impossible to meet simultaneously. The Navy wanted a fighter capable of 320 miles per hour, able to climb to 10,000 feet in 3.5 minutes, with a range exceeding 1,200 miles, exceptional maneuverability superior to any existing fighter, and armament consisting of 2 20mm cannons plus 2 machine guns. Designer Jiro Horikoshi faced a fundamental engineering challenge. Carrier operations demanded lightweight construction for catapult launches and arrested landings on short flight decks. Extended range required substantial fuel capacity. Heavy armament added weight. Strong airframe construction added more weight. Performance demanded a powerful engine, but Japan's industrial base couldn't produce engines matching American or British capabilities. The most powerful available engine, the Nakajima Sakai, generated only 840 horsepower at takeoff power. American and British fighters were using engines producing 1100 to 1400 horsepower. Horikoshi made calculated decisions about what to sacrifice. He employed an ultra-lightweight aluminum alloy called extra super duralumin, reducing structural weight to unprecedented levels. He eliminated armor protection entirely. No armored seat back for the pilot. No armored glass windscreen. No protective plating around vital components. He designed fuel tanks without self-sealing capability, saving weight but making the aircraft catastrophically vulnerable to incendiary rounds. He built the lightest airframe structurally capable of withstanding the stresses of carrier operations and aerial combat, with minimal safety margins. The result was extraordinary. The prototype A6M first flew on April 1, 1939. With the more powerful Nakajima Sakai A12 engine installed, the production A6M exceeded specifications. It could reach 346 miles per hour. It climbed to 10,000 feet in under 4 minutes. It had an operational range of 1,600 miles with external fuel tanks. The empty weight was just 3,904 pounds. A contemporary American fighter, the Grumman F-4F Wildcat, weighed 5,500 pounds empty. This weight advantage translated directly into performance advantages that stunned Western observers when the Zero entered combat. The aircraft could outturn anything in the sky. It could outclimb most opponents. It had sufficient range to escort bombers on missions that seemed impossible for single-engine fighters. Japanese pilots praised its responsiveness, light control forces, and forgiving handling characteristics. The Zero entered service with the Imperial Japanese Navy in July 1940, designated the Type 0 carrier fighter. The name derived from the Japanese imperial year 2600, which corresponded to 1940 in the Western calendar. Initial combat deployment came in China, where Zeros achieved immediate air superiority. Chinese forces had no effective counter to the new fighter. Soviet-supplied I-15 and I-16 fighters were outclassed. The Zero established kill ratios exceeding 12-1. This success in China created dangerous assumptions within Japanese military leadership. The victories confirmed beliefs about the superiority of Japanese fighting spirit and tactical excellence. They validated the design philosophy of accepting vulnerability in exchange for performance. Chinese forces lacked modern anti-aircraft artillery, heavy machine guns, or fighters with armor protection. The Zero's weaknesses never manifested in combat. When war erupted across the Pacific on December 7, 1941, Zeros participated in the Pearl Harbor attack, achieving complete surprise and suffering minimal losses. In the Philippines, Zeros decimated American air forces. In Malaya, they swept British opposition from the skies. In the Dutch East Indies, they dominated completely. Allied pilots reported the Zero with a mixture of fear and respect. Combat reports described an aircraft that seemed impossible. It was faster than Allied fighters, more maneuverable, longer ranged, better armed at close range with its 20mm cannons. The psychological impact extended beyond pilot reports. Newspaper accounts in America and Britain portrayed the Zero as evidence of unexpected Japanese technological sophistication. Intelligence analysts struggled to explain how Japan, a nation perceived as technologically inferior to Western powers, had produced such an advanced aircraft. Theories ranged from German technical assistance to espionage-acquired American technology. American pilots facing Zeros developed deep respect bordering on fear. The aircraft seemed unbeatable in turning combat. Wildcats couldn't match its maneuverability. They couldn't outrun it in level flight. They couldn't outclimb it. Early combat. Encounters produced casualty ratios favoring the Japanese. At the Battle of the Coral Sea in May 1942, combat results were roughly even. But even achieving parity represented an accomplishment against the Zero's performance advantages. This was the context when the Akutan Zero arrived at North Island. American pilots believed they faced a technologically superior opponent. They assumed Japanese engineering had achieved breakthroughs in lightweight construction and aerodynamic efficiency. They prepared to learn the secrets of advanced enemy technology. Understanding what American test pilots discovered requires understanding what they expected to find. 1942 represented a moment of genuine uncertainty about technological competition between industrial powers. Germany had demonstrated unexpected capabilities with advanced aircraft designs, rocket weapons, and jet engine development. Japan's early war victories suggested comparable technological sophistication. The Zero's performance specifications supported this assessment. American engineers examining wreckage recovered from Pearl Harbor and early Pacific battles documented the aircraft's construction. The aluminum alloy exhibited excellent strength to weight characteristics. The flush riveted skin demonstrated manufacturing precision. The wing design incorporated advanced features. The engine, while less powerful than American equivalents, operated reliably under demanding conditions. What remained unknown was the complete picture of design trade-offs. Wreckage analysis revealed the absence of armor protection, but this alone didn't fully explain the aircraft's vulnerability profile. Self-sealing fuel tanks were absent, a known weakness. But American intelligence analysts couldn't determine from wreckage examination how the entire structural design philosophy balanced protection against performance. Japanese design methodology differed fundamentally from American and British approaches. Western fighters incorporated progressive layers of protection. Armor plate behind the pilot's seat provided protection against rear attacks. Armored glass windscreens stopped small-caliber rounds from frontal attacks. Self-sealing fuel tanks contained multiple layers of rubber and fabric that swelled when punctured, sealing holes and preventing fuel leakage. Critical components received armored shields. Redundant control systems provided backup if primary systems were damaged. These protective measures added substantial weight. A typical armor installation in an American fighter included a seatback plate weighing approximately 40 pounds, armored glass adding 12 pounds, fuel tank self-sealing systems, adding weight proportional to tank capacity, and various protective covers and shields, adding another 20 to 30 pounds. Total protective weight often exceeded 100 pounds. Japanese designers eliminated all of it. The decision was neither careless nor uninformed. Horikoshi and his engineering team understood the trade-offs explicitly. They calculated that eliminating protective weight while maintaining structural integrity would provide performance advantages exceeding the tactical disadvantages of increased vulnerability. The assumption was that superior performance would allow Japanese pilots to control engagement conditions, attacking from advantageous positions and disengaging before suffering damage. This philosophy reflected broader Japanese military doctrine emphasizing offensive action. Training focused on aggressive tactics, precise gunnery, and situational awareness to avoid defensive situations. The aircraft design supported this approach. Everything about the Zero optimized offensive capability. Excellent visibility from the cockpit allowed pilots to spot enemies early. Maneuverability enabled positioning for attack. Sufficient armament provided killing power at close range. Extended range allowed pursuing retreating opponents or withdrawing before reinforcements arrived. The doctrine worked brilliantly against opponents using similar philosophies or lacking capability to exploit the Zero's weaknesses. Chinese pilots flying inferior aircraft couldn't capitalize on vulnerabilities. Early Allied opposition in the Pacific, surprised and outnumbered, fought defensively and suffered accordingly. But the doctrine contained fatal assumptions about the nature of the war Japan was fighting. American industrial capacity was producing fighters, incorporating lessons learned from the Battle of Britain and early European combat. Protection mattered. Pilot survival mattered. Aircraft that could sustain battle damage and return home mattered. American doctrine increasingly emphasized coordinated tactics, mutual support, and fighting from positions of strength, rather than individual pilot skill in knife-fight-turning combat. The captured Zero at North Island represented an opportunity to validate or refute assumptions on both sides. Japanese designers assumed their trade-offs produced a fighter optimized for the Pacific War's requirements. American intelligence assumed they faced advanced enemy technology, requiring new tactical approaches or superior aircraft to counter effectively. Sanders taxied the Zero to the runway that September morning, carrying the expectations of an entire theater of war. American pilots needed to know how to fight this aircraft. They needed weaknesses to exploit. They needed confirmation that better tactics or better aircraft could overcome the Zero's performance advantages. What Sanders discovered in the first minutes of flight would exceed anyone's expectations, but not in the way the Americans anticipated. Lieutenant Commander Eddie Sanders completed 24 test flights between September 20th and October 15th, 1942. Each flight revealed new information about the Zero's characteristics, capabilities, and critically, its limitations. Sanders methodically documented every aspect of the aircraft's performance, creating the most comprehensive evaluation of enemy equipment yet achieved in the Pacific War. The first revelation came during the initial climb. The Zero ascended rapidly, demonstrating the exceptional climb rate that had allowed Japanese pilots to gain altitude advantage in combat. At 200 miles per hour indicated airspeed, the aircraft felt responsive and light. Control forces were minimal. The stick required almost no pressure to initiate maneuvers. For a pilot accustomed to American fighters with their heavier, more solid feel, the Zero seemed almost toy-like in its responsiveness. But as Sanders increased speed, something unexpected happened. Above 200 knots indicated airspeed, the ailerons became progressively stiffer. At 230 knots, rolling the aircraft required significant force on the control stick. The light, nimble fighter that could snap roll instantly at lower speeds became sluggish and resistant at combat speeds typical of modern air warfare. American fighters regularly fought at speeds between 250 and 300 knots. At those speeds, the Zero's roll rate decreased dramatically. Sanders documented this carefully. The aircraft rolled more easily to the left than to the right, a characteristic caused by propeller torque effects and control surface design. An American pilot being pursued by a Zero could exploit this asymmetry. Rolling hard to the right at high speed would allow the American fighter to evade, while the Zero struggled to follow the maneuver. The second critical discovery came during negative G maneuvers. Sanders pushed the stick forward abruptly, creating negative gravitational forces. The Nakajima Sakai engine coughed, sputtered, and died. The propeller continued windmilling, but the engine produced no power. Sanders waited several seconds. The engine restarted as positive G-forces returned. He repeated the test, multiple times with identical results. The cause was the engine's float-type carburetor. Unlike American aircraft equipped with pressure carburetors or fuel injection systems, the Zero's engine relied on a simple float mechanism to regulate fuel flow. Under negative acceleration, fuel couldn't flow properly to the engine. The float chamber design, adequate for normal flight conditions, failed completely during negative G maneuvers. This weakness was tactically devastating. American pilots being pursued by Zeros could push over into a dive, creating negative G forces. The Zero's engine would quit. The pursuing Japanese fighter would lose power at the critical moment of engagement. By the time the Zero's engine restarted, the American aircraft would have opened distance and potentially reversed the engagement geometry. Sanders tested the Zero against multiple American fighter types in mock combat. A Lockheed P-38F Lightning participated in comparison flights. The twin-engine P-38, climbed more slowly than the Zero initially, but accelerated away in level flight above 200 miles per hour. The Zero couldn't catch a P-38 that maintained high speed and avoided turning combat. A Bell P-39D Airacobra flew against the Zero. The P-39, generally considered inferior to frontline fighters, still demonstrated advantages at high speed. The Zero outturned it easily at low speeds but couldn't follow high-speed maneuvers. A Curtiss P-40F Warhawk, the standard Army Air Forces fighter in the Pacific during early 1942, showed similar results. The Zero possessed superior maneuverability and climb performance, but the P-40 could dive away, accelerate in level flight, and avoid situations where the Zero's advantages mattered. A North American P-51 Mustang, just entering service, outperformed the Zero in every category except turn radius at low speeds. The Mustang was faster, climbed better at high altitudes, dove faster, and could sustain higher G-forces in maneuvering combat. Most significantly, Sanders flew the Zero against the Grumman F-4F Wildcat and Vought F-4U Corsair, the Navy's primary fighters. The Wildcat, which had fought Zeros to rough parity in early combat, showed clear paths to advantage. Maintaining speed above 250 knots eliminated most of the Zero's maneuvering advantage. Using diving attacks and avoiding sustained turning combat negated the Zero's strengths while exploiting its weaknesses. The Corsair, with its powerful 2,000 horsepower Pratt & Whitney R2800 engine, dominated the Zero in every performance category except low-speed turn radius. A Corsair pilot who maintained speed and used vertical maneuvers could control the engagement completely. But the most shocking discovery came not from flight testing, but from ground examination of the aircraft's structure. Engineers at North Island conducted detailed inspection of the airframe, measuring component thicknesses, analyzing material properties, and evaluating structural design. The fuselage skin measured 21 thousandths of an inch thick. American fighters typically used skin thickness between 32 and 40 thousandths of an inch. The Zero's skin was approximately 1/3 thinner. Wing skin showed similar characteristics. The aircraft was built to minimum structural standards, with no safety margins for battle damage. Engineers examined the fuel tanks. No self-sealing capability existed. A single puncture would allow fuel to drain freely. Tracer rounds or incendiary ammunition would ignite fuel instantly. The Japanese had installed some fire suppression equipment, but it was rudimentary compared to American systems. The cockpit contained no armor whatsoever. The pilot's seat was unprotected. No armored glass shielded the windscreen. No protective plates covered vulnerable components. A bullet entering the cockpit would encounter only the pilot and the delicate aircraft structure beyond. American ordnance specialists conducted ballistic tests. They wanted to know what weapons could defeat the Zero's structure. The tests revealed something that would fundamentally change how American pilots approached combat against Japanese aircraft. The ballistic testing program at Naval Air Station North Island proceeded systematically through various weapon types. Ordnance specialists needed quantitative data about the Zero's vulnerability to different ammunition types and calibers. They set up controlled tests, firing at sections of Zero airframe material from measured distances using standard American weapons. They began with rifle-caliber ammunition. 30 caliber ball rounds, the standard infantry rifle cartridge, penetrated the thin skin easily at ranges exceeding 300 yards. The 21 thousandth inch aluminum alloy provided essentially no protection against rifle fire. 30 caliber armor-piercing rounds went through the skin and continued with sufficient energy to damage internal components. The tests proceeded to aircraft machine gun ammunition. The 30 caliber ANM-2 Browning aircraft machine gun, standard armament on many American fighters, fired at higher velocities than infantry rifles. 30 caliber armor-piercing incendiary rounds, designed to ignite fuel tanks and ammunition, penetrated the Zero's structure effortlessly. At typical combat ranges of 300 to 500 feet, The rounds went completely through the airframe, entering one side and exiting the other. Then the specialists tested 50 caliber ammunition. The M2 Browning heavy machine gun fired a 12.7mm round at muzzle velocities exceeding 2,900 feet per second. Armor-piercing 50 caliber ammunition was designed to defeat light armor plate up to half an inch thick at close range. The results shocked everyone present. 50 caliber armor-piercing rounds didn't just penetrate the Zero's skin. They tore through it as if the aluminum alloy were paper. At 200 yards, the rounds punched clean holes through the fuselage, with energy remaining to continue through internal structure. At 300 yards, penetration was still complete and decisive. At 500 yards, the rounds still defeated the skin easily, though with slightly reduced post-penetration effects. The test engineers examined the entry and exit holes carefully. Entry holes were relatively clean, approximately half an inch in diameter, slightly larger than the bullet diameter due to metal deformation. Exit holes were larger and more ragged, typically 3/4 of an inch to 1 inch across, as the bullet tore through the material from the inside. They tested different sections of the airframe. The engine cowling provided minimal protection. The firewall between engine and cockpit was thin sheet metal. 50 caliber rounds went through it completely. The cockpit area, including the sides and rear of the pilot's position, offered no protection. A burst from a 50 caliber machine gun aimed at the cockpit would be lethal to the pilot with absolute certainty. The fuel tanks, located in the fuselage ahead of the cockpit and in the wings, were completely vulnerable. A single 50 caliber incendiary round striking a fuel tank would penetrate, ignite the fuel, and create catastrophic fires. The lack of self-sealing meant fuel would drain from the puncture while burning, spreading fire throughout the internal structure. Engineers calculated the practical implications. An F4F Wildcat carried 6 50 caliber machine guns with approximately 240 rounds per gun. Total ammunition load was 1,440 rounds. Rate of fire was approximately 750 rounds per minute per gun, meaning all 6 guns together fired 4,500 rounds per minute. A 1-second burst from all 6 guns discharged 75 rounds, even accounting for accuracy limitations in combat conditions. A 1-second burst from a Wildcat at 300 feet range would place multiple 50 caliber rounds into a Zero-sized target. Each hit would penetrate completely. Hits on the fuel tanks meant fire. Hits on the cockpit meant pilot casualties. Hits on control surfaces meant structural failure. The Zero simply could not withstand even brief exposure to 50 caliber fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The F4U Corsair carried the same armament, 6 50 caliber machine guns, but with even more ammunition. The Corsair's higher speed and better high-altitude performance meant it could engage Zeros from positions of advantage more easily than the Wildcat. American engineers compared these findings to what they knew about American fighter construction. The F4F Wildcat's fuselage skin measured 32 to 40 thousandths of an inch thick, roughly twice the Zero's thickness. The Wildcat had armor plate behind the pilot's seat, a thick steel plate capable of stopping 50 caliber rounds from the rear hemisphere. The windscreen incorporated armored glass that could stop 30 caliber fire from frontal attacks. The Wildcat's fuel tanks included self-sealing construction. Each tank consisted of multiple layers: an inner rubber layer, fabric reinforcement, a vulcanized rubber outer layer, and a protective cover. When punctured, the rubber layers swelled, sealing holes and preventing fuel leakage. While not invulnerable, self-sealing tanks dramatically reduced fire risk compared to unprotected tanks. American fighters could absorb battle damage and continue fighting. Multiple documented cases existed of Wildcats returning to carriers with dozens of bullet holes, damaged control surfaces, and wounded pilots still flying the aircraft. The robust construction and protective systems kept aircraft and pilots alive through damage that would destroy a Zero instantly. The Zero's design philosophy became clear through this analysis. Japanese engineers had sacrificed every element of protection to minimize weight and maximize performance. The aircraft was optimized for offensive action by skilled pilots who controlled engagement geometry. It assumed Japanese pilots would see enemies first, attack from advantageous positions, and disengage before suffering return fire. But that assumption failed against American tactics evolving through 1942. American fighter doctrine increasingly emphasized mutual support, coordinated attacks, and fighting from strength rather than individual pilot skill in turning combat. The Thatch-Weave maneuver, developed by Lieutenant Commander John Thatch, used pairs of fighters weaving back and forth to provide mutual cover. When a Zero attacked one American fighter, the other was positioned to attack the Zero from its vulnerable position. American radar direction, improving throughout 1942, allowed fighters to intercept Japanese formations with altitude advantage. Starting above the enemy meant American fighters could dive to attack, using their superior high-speed performance and maintaining energy advantage throughout the engagement. The captured Zero's evaluation provided the missing piece of tactical understanding. American pilots now knew exactly how to exploit their aircraft's advantages while avoiding situations where the Zero's strengths mattered. The intelligence reports generated from the Akutan Zero evaluation reached operational units throughout the Pacific during late 1942 and early 1943. Informational Intelligence Summary No. 59, published before the first test flight, contained preliminary information from examination of Zero wreckage. Informational Intelligence Summary No. 85, published in December 1942, contained comprehensive results from Sanders flight tests and comparative evaluations. Technical Aviation Intelligence Brief No. 3 provided detailed tactical recommendations based on the test results. The document stated explicitly that the Zero's advantages were limited to low-speed maneuvering combat. It recommended that American pilots maintain speeds above 300 miles per hour, indicated whenever possible. It emphasized the Zero's poor roll rate at high speeds and vulnerability during negative G maneuvers. Most critically, the intelligence reports confirmed that standard American armament was more than adequate to destroy Zeros. Pilots didn't need specialized weapons or tactics to defeat the Zero's structure. The 50 caliber machine guns they already had were devastating against the lightly built Japanese fighter. Marine Captain Kenneth Walsh, who eventually achieved 17 confirmed victories against Zeros, described how he used information from the Zero test flights. Flying an F-4U Corsair, he encountered a Zero on his tail during combat operations. Walsh executed a split S maneuver, rolling inverted and pulling through to a vertical dive. His Corsair accelerated rapidly, reaching 260 knots. Walsh then rolled hard to the right. The Zero attempted to follow but couldn't match the Corsair's roll rate at high speed. The Japanese pilot rolled left instead, trying to use the Zero's better roll performance in that direction. But Walsh had already reversed his turn, rolling right again. The Zero couldn't track the rapid directional changes. Walsh extended away from the Zero, opened range to a safe distance, then reversed to attack. A brief burst from his 650 caliber guns struck the Zero's wing root and fuselage. The Japanese fighter began burning immediately. The pilot never escaped. Walsh's engagement demonstrated the practical application of intelligence from the captured Zero. He maintained high speed to negate the Zero's turn advantage. He used high-speed rolls to the right, exploiting the Zero's weakness in that direction. He attacked only when positioned advantageously. His 50 caliber guns destroyed the Zero with a single burst because the aircraft's structure couldn't withstand that firepower. Similar reports came from Navy and Marine squadrons throughout the Pacific. Pilots who had previously feared the Zero's capabilities now approached combat with confidence. They understood their aircraft's advantages. They knew the Zero's vulnerabilities. Most importantly, they knew their standard armament could destroy Zeros reliably if they achieved firing position. The psychological shift was as important as the tactical revelations. American pilots had fought the first year of the Pacific War, believing they faced technologically superior opponents. The mystique surrounding the Zero contributed to Japanese early successes as much as the aircraft's actual capabilities. Pilots expecting to face an invincible enemy fought cautiously, defensively, accepting disadvantageous situations rather than pressing attacks aggressively. The captured Zero destroyed that mystique completely. American pilots learned the Zero was not a technological marvel. It was a lightweight fighter with excellent low-speed maneuverability gained by eliminating everything that made aircraft survivable in modern combat. It had no armor, no self-sealing tanks, no structural strength to resist battle damage. It was vulnerable to any weapon heavier than a rifle. Navy and Marine squadrons adjusted their tactics based on the intelligence reports. Fighter directors used radar to vector fighters to intercept Japanese formations with altitude advantage. Pilots avoided low-speed turning combat, instead using high-speed slashing attacks. They worked in pairs or larger formations, providing mutual support and preventing Zeros from isolating individual aircraft. The statistical results reflected these tactical changes. During the Battle of the Coral Sea in May 1942, American fighters achieved roughly even exchange rates against Zeros. By the Guadalcanal campaign starting in August 1942, American kill ratios improved steadily. By early 1943, Navy and Marine pilots were achieving kill ratios exceeding 5-to-1 against Zeros. The improvement wasn't primarily due to new aircraft, though the F-6F Hellcat and refined F-4U Corsair models entering service in 1943 were superior to earlier American fighters. The improvement came from understanding how to fight the Zero effectively using existing aircraft and tactics informed by comprehensive knowledge of the enemy's strengths and weaknesses. Japanese pilots began reporting that American tactics had changed. Instead of engaging in turning combat where the Zero's maneuverability provided advantage, American fighters dove to attack at high speed, fired brief bursts, then extended away before the Zero could respond. When Zeros pursued, American fighters used negative G pushovers to kill the Zero's engine, then reversed to attack the now powerless Japanese aircraft. Japanese ace Saburo Sakai, one of the highest-scoring IJN pilots who survived the war, later wrote about the changing nature of air combat in the Pacific. He described how American pilots who had initially fought poorly became progressively more difficult opponents. They stopped trying to outturn Zeros. They used their aircraft's advantages ruthlessly. They fought in coordinated formations that the Zeros, lacking radios in most aircraft, couldn't counter effectively. Sakai noted particularly the devastating effectiveness of American .50 caliber machine guns. He wrote about watching Zeros disintegrate under brief bursts of fire that seemed impossibly destructive. Sakai himself survived numerous combats only through exceptional skill and some luck, repeatedly nursing badly damaged aircraft back to base. Many of his squadron mates died when single bursts from American fighters ignited their fuel tanks or killed them instantly in their unprotected cockpits. The intelligence gained from the Akutan Zero spread beyond Navy and Marine aviation. Army Air Forces units in the Pacific received the same tactical intelligence summaries, P-38. Lightning pilots learned to exploit their twin-engine fighters' high-speed advantages against Zeros. P-40 pilots, flying aircraft generally considered inferior to the Zero in performance, learned they could compete effectively by maintaining speed and avoiding the Zero's strengths. The Akutan Zero continued serving American intelligence needs throughout 1943 and into 1944. After Sanders completed his initial test flights, Navy test pilot Lieutenant Melvin C. Hoffman conducted additional evaluations, flying mock combat against recently commissioned Navy pilots to train them in Zero capabilities and vulnerabilities. The aircraft traveled to Washington National Airport in 1943 for public display as a war prize, demonstrating to American civilians that Japanese equipment could be captured and analyzed. In 1944, the Zero returned to North Island for use as a training aircraft. Rookie pilots being sent to the Pacific flew against it in practice engagements, learning firsthand how to exploit its weaknesses. A second captured Zero, a Model 52 variant recovered during the liberation of Guam, joined the training program, providing comparison between early and late-war Zero models. The Akutan Zero's service ended abruptly in February 1945. While taxiing for takeoff at North Island, a Curtiss SB-2C Helldiver dive bomber lost control and collided with the Zero. The Helldiver's propeller sliced through the Zero's fuselage, destroying the irreplaceable aircraft. Navy photographer William N. Leonard salvaged several gauges and instruments from the wreckage, which he later donated to the National Museum of the United States Navy. Small pieces of the aircraft reside in the Alaska Aviation Heritage Museum and the Smithsonian National Air and Space Museum, but the aircraft's physical destruction mattered little by February 1945. The intelligence it provided had already transformed Pacific air combat. The tactical recommendations derived from testing the Akutan Zero had been distributed throughout American naval and Army aviation. Thousands of pilots had been trained using knowledge gained from that single captured aircraft. The mystique of Zero invincibility had been shattered completely. For Japanese pilots still flying Zeros in the war's final year, the situation had become desperate. American fighters had evolved far beyond the F-4F Wildcats that had struggled against Zeros in early 1942. The Grumman F-6F Hellcat, designed with explicit knowledge of Zero capabilities and weaknesses, entered service in mid-1943. The Hellcat was faster than the Zero, climbed better, dove faster, and carried 650 caliber machine guns plus armor protection and self-sealing tanks. The refined F-4U Corsair, with its distinctive inverted gull wing and powerful 2,000 horsepower engine, dominated Zeros completely. Corsair pilots could choose when and how to engage. They could attack from any angle, certain their 50 caliber guns would destroy Zeros with brief bursts. They could absorb return fire that would be fatal to Zero pilots. The statistical dominance was overwhelming. F-6F Hellcats achieved kill ratios exceeding 19-1 against all Japanese aircraft types, with Zeros comprising the majority of targets. F-4U Corsairs achieved similar ratios. Even the older F-4F Wildcats, relegated to escort carrier duty by 1944, achieved final kill ratios approaching 7-1 against Zeros, as pilots applied lessons learned from the captured aircraft evaluation. Japanese industry attempted to address the Zero's vulnerabilities in later variants. The A6M model, introduced in late 1943, featured thicker wing skinning to permit higher diving speeds. The A6M5B variant added a 45mm armored glass windscreen and a fuel tank fire extinguisher system. The A6M5C model included an 8mm armor plate behind the pilot's seat and additional armored glass. But these improvements came too late and added weight that degraded the Zero's performance advantages. The A6M5C weighed approximately 600 pounds more than the original A6M2, reducing climb rate and maneuverability, while only marginally improving survivability. A 50 caliber burst could still destroy an A6M5C. The armor protected against some attack angles but remained inadequate against the concentrated firepower of American fighters. More critically, Japan's industrial capacity could not produce advanced replacement fighters in sufficient numbers. The Kawanishi N1K-2J Shidenkai, a genuinely capable late-war fighter with adequate armor and self-sealing tanks, entered production in late 1944, but only 415 were built before war's end. The Mitsubishi J2M Raiden Interceptor, designed specifically to combat B-29 bombers, achieved limited production with only 476 completed. Japan produced approximately 10,500 Zeros during the war, more than any other Japanese aircraft type. But this production figure paled compared to American output. The United States produced over 12,000 F-6F Hellcats, over 12,000 F-4U Corsairs, and continued producing improved variants of earlier types. American industry could replace losses immediately while introducing new types with better performance. The disparity extended beyond numbers to pilot training. Japan's experienced cadre of naval aviators, the elite pilots who had achieved early victories in Zeros, died progressively throughout 1942 and 1943. The Guadalcanal campaign consumed experienced pilots at unsustainable rates. By mid-1943, average Japanese pilot training had decreased from over 700 flight hours before Pearl Harbor to less than 200 hours by war's end. American pilot training improved consistently. Pilots reached combat units with 300 to 500 flight hours, extensive gunnery training, and tactical instruction based on combat reports and intelligence about enemy capabilities. They flew superior aircraft with better radios, better gun sights, and better survival equipment. When hit, they often survived, recovered, and returned to combat with added experience. The story of the captured Zero illuminates fundamental truths about industrial warfare between modern nations. The Pacific War was decided not primarily by individual weapons systems or tactical innovations, but by systematic advantages in industrial capacity, pilot training, sustainability, and design philosophy, reflecting different national resources and strategic circumstances. Japan's aircraft industry employed approximately 350,000 workers at peak wartime production. American aircraft industry employed over 2 million workers. This 10-to-1 disparity in industrial workforce translated directly into production capacity differences. American factories produced over 300,000 aircraft during World War II. Japan produced approximately 76,000 aircraft total, less than 1/4 of American output. The Zero represented Japanese industry's best effort to produce a world-class fighter with available resources and technology. The design compromises weren't mistakes or oversights. They were calculated decisions about how to achieve required performance with available engine power and within weight constraints necessary for carrier operations. Eliminating armor and self-sealing tanks wasn't carelessness. It was the only way to achieve the Navy's performance. Specifications with an 840 horsepower engine. American designers faced no such constraints. The Wright R-1000, 820 Cyclone powering the F-4F Wildcat produced 1,200 horsepower. The Pratt & Whitney R-2000 800 Double Wasp powering the F-6F Hellcat and F-4U Corsair produced 2,000 to 2,300 horsepower depending on variant. With more powerful engines available, American designers could add armor protection, self-sealing tanks, heavier armament, and robust structure while maintaining competitive performance. The difference reflected broader economic realities. American industry could produce powerful aircraft engines in quantity. Japan could not. American aluminum production in 1944 exceeded 500,000 tons annually. Japan's aluminum production peaked at approximately 140,000 tons annually. American aviation gasoline production was effectively unlimited. Japan struggled constantly with fuel shortages, as American submarines interdicted tanker routes from Southeast Asian oil fields. These resource disparities shaped aircraft design fundamentally. American fighters were built robustly because American industry could afford the weight penalty. Japanese fighters were built lightly because Japanese industry had no alternative. The Zero's vulnerabilities weren't design flaws in the conventional sense. They were inevitable consequences of Japan's resource constraints and strategic situation. What the captured Zero revealed to American intelligence was that Japanese industry had reached the limits of what was possible with available resources. There was no secret superweapon waiting to deploy. There was no revolutionary technology that would restore Japanese air superiority. The Zero represented the best Japan could produce, and American industry could overwhelm it through sheer material superiority. This realization had strategic implications beyond tactical air combat. If Japan's best fighter was vulnerable to standard American weapons, if Japanese industry couldn't match American production rates, if Japanese pilot training couldn't sustain combat losses, then the war's outcome was predetermined by industrial capacity rather than fighting spirit or tactical excellence. Japanese military leadership understood this at some level. Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack, had lived in the United States and understood American industrial might. He reportedly stated that Japan could run wild for 6 months to a year, but had no confidence in success in a protracted war. The capture and evaluation of the Akutan Zero confirmed Yamamoto's assessment. By mid-1943, Japan was losing the industrial competition decisively. American shipyards were producing Essex-class fleet carriers at a rate Japan couldn't match. American aircraft factories were producing thousands of fighters monthly, while Japanese production struggled to replace combat losses. American pilot training schools were graduating thousands of aviators, while Japanese training programs contracted under fuel shortages and equipment limitations. The Zero, once symbol of Japanese technological prowess and military effectiveness, became symbol of Japan's industrial limitations. Every Zero shot down represented irreplaceable losses of pilot experience and aircraft production capacity. Every American fighter lost was replaced within weeks by a newer, better aircraft flown by a fresh pilot with comprehensive training. The psychological impact on Japanese aviators was devastating. Pilots who had fought confidently in 1942, secure in their aircraft's superiority and their own skill, found themselves progressively overwhelmed by superior numbers of increasingly capable American fighters. The knowledge that their aircraft offered essentially no protection against American .50 caliber guns created constant stress. Every combat sortie meant potential, instant death from a single burst of fire. Some Japanese pilots survived dozens of combat missions through exceptional skill and luck. Saburo Sakai flew combat missions from 1941 through August 1943, when severe wounds forced his retirement from frontline service. He survived by never making mistakes, by constantly maintaining situational awareness, by understanding his aircraft's limitations, and never exceeding them. Most Japanese pilots lacked Sakai's exceptional abilities. They died within weeks or months of reaching combat units, killed by American pilots flying superior aircraft with better training and overwhelming numerical advantage. By 1944, Japan committed Zeros to kamikaze operations. The aircraft that had dominated Pacific skies in 1942 became one-way suicide weapons. Pilots with minimal training flew Zeros, loaded with bombs directly into American ships, sacrificing themselves because conventional combat had become hopeless. Over 2,500 kamikaze attacks during the war's final year testified to Japanese desperation and the complete collapse of their conventional air power. The morning Eddie Sanders flew the captured Zero at North Island, he couldn't have anticipated the full implications of what he would discover. He expected to learn about an advanced enemy aircraft, to document its performance characteristics, to identify tactical weaknesses American pilots could exploit. What he actually discovered was more profound and more consequential. Sanders learned that the Zero represented not Japanese technological superiority, but Japanese industrial desperation. Every aspect of the aircraft's design reflected compromises forced by resource limitations and strategic circumstances. The thin skin, the absent armor, the vulnerable fuel tanks, these weren't oversights. They were calculated sacrifices necessary to achieve performance specifications with inadequate engine power and limited production capacity. The intelligence derived from that single captured aircraft transformed American understanding of the Pacific Air War. Pilots stopped fearing the Zero as an invincible superweapon and started recognizing it as what it actually was: a lightweight fighter optimized for specific conditions, vulnerable to standard American weapons, and representative of an enemy that couldn't match American industrial might. The tactical recommendations distributed throughout the Pacific Fleet saved countless American lives. Pilots who maintained speed and avoided the Zero's strengths while exploiting its weaknesses survived combats they might otherwise have lost. The psychological boost of knowing American .50 caliber guns could destroy Zero's reliably improved pilot confidence and aggressiveness. American air superiority in the Pacific, established progressively through 1943 and 1944, rested partly on knowledge gained from Koga's Zero. For Tadayoshi, Koga, the 19-year-old pilot who died when his Zero flipped on Akutan Island's boggy landing field, the crash landing had consequences extending far beyond his personal tragedy. His death, instantaneous when the impact broke his neck, prevented him from destroying the aircraft per standing orders. His wingmen's decision not to strafe the apparently intact Zero, hoping Koga might have survived, preserved the aircraft for American recovery. These chance circumstances delivered to American intelligence the single most valuable piece of captured equipment from the Pacific War. Koga was buried initially on Akutan Island by the American recovery team that found his body in the wreckage. In 1947, an American Graves Registration Service team exhumed his body and reburied it on Adak Island with other recovered Japanese remains. The team, unaware of his identity, marked the grave as an unknown Japanese soldier. In 1953, during repatriation of war dead, his body was likely exhumed again and returned to Japan for cremation, though definitive records don't exist. Koga's family learned nothing definitive about his fate for years after the war. They knew only that he had been lost during the Aleutian campaign. They didn't know that his aircraft had provided Americans with intelligence that fundamentally altered the Pacific Air War. They didn't know his death had contributed inadvertently, but significantly, to Japanese defeat in the air. The broader lesson extends beyond World War II air combat. The Zero story illustrates how technological competition between nations reflects underlying economic and industrial realities. Superior design cannot overcome fundamental resource disadvantages indefinitely. Japan's engineers were highly skilled, but skill alone couldn't compensate for lack of powerful engines, limited aluminum production, and inadequate industrial workforce. American victory in the Pacific resulted from systematic advantages, compounding over time. Better industrial capacity produced more aircraft, better training programs produced more pilots, better logistics provided more fuel, ammunition, and spare parts. Better technology, enabled by superior resources, produced aircraft with performance advantages and protective systems that kept pilots alive. These advantages multiplied throughout the war, while Japanese advantages eroded progressively. The captured Zero provided dramatic evidence of these underlying realities. American test pilots and engineers examining the aircraft saw clearly that Japan was fighting an industrial war with inadequate industry. The thin skin, the absent armor, the minimal structure, all testified to resource constraints that superior tactics or fighting spirit couldn't overcome. When Sanders landed after his first flight in the Zero, he had discovered something more important than tactical vulnerabilities or performance limitations. He had discovered that American fears of Japanese technological superiority were unfounded. The mystique surrounding the Zero, built through early combat successes and reinforced by effective propaganda, dissolved under systematic analysis. What remained was the reality: a lightweight fighter built to minimum standards, vulnerable to standard weapons, representative of an enemy that was already losing the industrial competition decisively. The war would continue nearly 3 more years after Sanders's first flight in the captured Zero. Thousands more would die in air combat over Pacific islands and seas. But the trajectory had become clear. American industry would produce increasingly superior aircraft in overwhelming numbers. American training would graduate pilots faster than combat consumed them. American tactics, informed by comprehensive intelligence about enemy capabilities, would achieve ever higher kill ratios. The Zero, symbol of Japanese air power at its peak, became symbol of Japanese industrial limitations at their most stark. Every remaining Zero in IJN service after mid-1943 was a target waiting to burn under American .50 caliber fire. The pilots flying them knew this. They fought anyway, with courage born of duty and nationalism, but they fought without illusions about their chances. The aircraft that had once seemed invincible had been revealed as tragically vulnerable, and that revelation changed everything. On that September morning in San Diego, when Sanders advanced the throttle and lifted the captured Zero into California skies, he opened a door to understanding that would help win the Pacific War. Behind the elegance of the Zero's lines and the excellence of its performance at low speeds lay the truth about industrial warfare. Material advantages matter more than fighting spirit. Production capacity trumps tactical excellence, and no amount of pilot skill compensates for flying an aircraft that cannot survive being hit. The Americans learned that lesson by capturing and testing Koga's Zero. The Japanese learned it through years of progressively desperate combat against opponents whose advantages grew continuously, while Japanese capabilities eroded. By war's end, the lesson was complete and undeniable. Industrial might, not individual weapons superiority, determines outcomes in modern warfare between nations. The Zero story proves that truth with clarity that remains relevant decades later. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.